Alright, we're dealing with rate problems in section 2.8. And you might be thinking, what do any of these problems have in common? They all have to do with rates. Cool. Okay, so we're going to start with the first type of problem in section 2.8, which has to do with a rate we're all quite familiar with, which is your speed, where you travel miles per hour. So that's the rate that's going on here. And the question is, how long will it take a bus traveling at 60 miles per hour to overtake a car traveling at 40 miles per hour if the car had a 1.5 hour head start? I would just like to say that I think this question is bollocks, because when do you see buses overtaking cars? But we will just go with it and say, right? Am I right? Why is a bus going to go 60 miles per hour if the car can only go 40? But anyway, I'm not going to get too upset over it. I'm going to just deal with the problems. The first thing that I have to look at is understanding what it means when they say overtake a car. So, meaning, if they both start in the same position, so let's say this is our starting point here. Starting point. So, and then the bus, or sorry, who goes first? Matt, who went first?
The car.
Oh, the car took off first. So if the car takes off first, and there's car driving. I can't draw a car, so I wrote car. When we're talking about when the bus will overtake the car, so car got a 1.5 hour head start, and it overtakes the car when it catches up to the car. So what do we know, Matt, about those distances?
They are the same.
They are going to be the same. So this is going to be our big idea for this question. It doesn't necessarily happen in all the distance problems that their rates, that their distances are the same. But in this case, that's what's going on. So the distance that the car travels is the same as the distance that the bus travels. And that's going to be our overarching theme for this problem. So the next thing is dealing with the actual rates. The car, we know that rate times time equals distance, right? So we have the car, and we have the bus, and the car is traveling at 40 miles per hour. I'm going to run out of room. And the bus is barreling down the road. I think it should get a ticket at a whopping 60 miles per hour. What do you think, Matt? Will they pull the bus over? Do you realize you are a bus and you cannot travel faster? But anyway, the car has been traveling for 1.5 hours longer than the bus. There's a couple ways to do this. First, you have to ask yourself which one's bigger, the car traveling time or the bus? And which one's bigger, Matt?
The car.
The car's been traveling longer because it started sooner. So if I called T the time that the bus has been traveling, the car's been traveling longer. T plus 1.5, and now my graph is looking a little sketchy, but that's okay. Now that we've got all this filled out in the table, we can use the formula. The rate times the time will give me the distance. So the car's, that was it back there. The car's distance will be 40 times t plus 1.5, and the bus will be 60 t. That represents the distance. The 60 t represents the distance the bus has traveled, and the 40 times the quantity t plus 1.5 represents the distance the car has traveled. What else was I going to say about that?
They should be the same.
Yeah, I wasn't going to go there yet. There's something else. Oh, you could also solve this problem over here. If I had said instead that the car had been t, then I could have written the bus as t minus 1.5. Amazingly, when you solve this equation, you would still get the right answer. Woohoo, go math. All right, so let's now put together our overarching themes back to this equation here. The distance the car has traveled, and remember the distance the car has traveled is 40t plus 1.5, and the distance the bus has traveled is 60t. So now we are going to have, 40, sorry, I need my pen, 40 times t plus 1.5 will be equal to 60t. Once you've got the right equation, you should be home free if you've been doing the work in the previous sections. 40 times 1.5 is going to give me 60. And then if I subtract the 40t on both sides, look, I'm going to do it in red. Oops, subtract that 40t. Okay, now I get what Shanoa was saying. I was like, subtract that 40t. And then we end up with 60 is equal to 20t. And so t is going to be equal to 3. Now remember, t was originally the time that the bus had been traveling. So the bus will overtake the car. I hope it lets me keep writing. 3 hours after it leaves the starting point. The starting point. I ran out of space. If they had asked you how many miles have they traveled, well, you could just go back up here. Remember, 60t is the distance that the bus has traveled. So if you plug the t equals 3 into the 60t, you'll get, Matt? That's right. Plug 3 into the t. You get 180. Okay, Matt is awake. Okay, you would get 180 miles. You would get the same thing if you plug that in over on the other side as well. Cool? Yay, so that's a distance problem. So the rate in this case is the speed. Moving on. We're going to wake Matt up and let him read the next question. Go ahead, Matt. I just want to hear you say that name.
I have no idea.
Karen, what a gal. That's how I'm going to say it. Karen, what a gal. Wagtall. Wagtall, I don't know. She's Karen.
Karen invested some money at 9% annual simple interest and $250 more than that amount at 10% annual simple interest. If her total yearly interest was $101, how much was invested at each rate?
Okay. Once again, another one of these problems where you're like, dude, Karen, you want to make more money, just put all your money in the 10%.
You'd
right?
think that,
right? But no. She's probably avoiding, like, going into an upper tax bracket or something. So there might be a reason she needs to split her money. But in the real world, if you want to make more money, who cares about the 9% account? So in this case, again, our rate in this is the interest rate. So these interest rates are a little easier to see. There's the 9% and there's the 10% interest rates of the two accounts. She invested some money, we don't know how much, at the 9% account. So let's just say X is the amount in the dollar amount, I would say. The dollar amount in the 9% account. And that's just a name for the account, the 9% account. And then if she invested $250 more than that amount at 10%, then X plus $250 would be the dollar amount in the 10% account. So realize, when you're told an interest rate, that means how much money, how much free money you're going to make in a year, depending on your principal. So your interest rate, your interest is always your principal, which is how much money you invest, times your rate, times your time. That will always give you your, oh yeah, I'm good, interest. Okay, so principal times rate times time will be your interest. So in one account, well, actually, first, let's look at the big thing. If her total yearly interest was $101, how much was invested at each rate? So her interest that she earned in the 9% account plus the interest that she earned in the 10% account should be her total interest. Unless she's got some offshore accounts she's not telling us about, which
Shady
often
Karen.
happens with Karen Wadagal. So this is going to be our overarching equation right here. How much I earn in the 9% plus how much I earn in the 10% will give me how much interest I earn total. So this is all in dollar amounts. Here's the dollar amount of money I earn here, dollar amount of money I earn there, and so on. So moving on. So the interest I earn in the 9%, if I have X dollars in the 9% account, the interest I'm going to make is 9% of X. And then in the other account, which I think I said from the previous slide, that was X plus 250. You put more money in that. The interest we earn in that account is going to be 0.1 times that. So you add these two accounts together, and you're going to make, was it 101?
101.
101. Good thing I got Matt here. Keep me honest. And there's my overarching equation. Remember, again, this expression right here, this is the interest I earned in dollars in the 9% account, and then over here is the interest I earned in dollars in the 10% account, and then over here is my total interest. Yay! They add together to be the same. I just like the arrows. If I were to ask you, what does X plus 250 represent? What would that represent? Just the X plus 250, Matt?
The amount of money you have in the 10% account?
The amount of principal you have in the 10% account, which you originally put into the 10% account. But when you multiply that by the 10%, now you're talking interest. Okay, so before you lose interest, I'm going to solve this. Sorry. It's late. What's 0.1 times 250? I can do that. Look at calculator at the ready. So 0.09 plus, that's going to be 0.19, right? Just watch me because I sometimes don't know what I'm doing. Okay. And now I'm going to subtract the 25. I'm going to use my red. Subtract that 25. And I got my 101 and subtract my 25. And I end up with 0.19x is equal to 76. I can do that. And now when I divide both sides by 0.19, I'm doing this because I would normally write another line, but I'm running out of room. So x is equal to 400. Is that right? Oh, cool. So what we've just shown, and I don't know what the original question, I should go back and look at what the original question asked for. Did it ask how much was in both accounts? I'm going to answer, I'm going to cover my bases and write $400 was invested. Notice you didn't make $400 in interest. You actually made, if you plug that 400 times 0.09, that's going to give you how much you made. What is that, $36 in interest? You made $36 in interest, but you originally invested $400 in the original account. So $400 was invested in the 9% account. I ran out of room, so but you can just see in the 10% you had $250 more, so you invested $650 in the 10% account. You can write that down because I ran out of room. Alright, so that's another rate problem using an interest rate. So notice that all of these problems, even in the rate times time, and this one, all of these problems involve there's a rate times a quantity, plus a rate times a quantity is equal to a final amount, or sometimes there's a rate times a quantity in here as well. Last problem, sorry this one's a little fuzzy. Some coin or money problems. Again, you don't really think of those as a rate, but the value of money is actually a rate. A dime is worth 10 cents every coin. So 10 cents a dime is actually a rate going on there. So in this one, you've got a collection of dimes and quarters. is retrieved from a soft drink machine. There are 5 times as many dimes as quarters, and the total value of the coins is blah, blah, 27. There's a lot going on here. So find the number of dimes and the number of quarters. So the overarching thing in this problem is your total value of the coins. So our overarching theme is going to be the value of the dimes plus the value of the quarters, like that, the quarters, is going to be the total value. Okay, so now we just have to figure out how many dimes, how many quarters, and so on, and what's their value. So we were told there are 5 times as many dimes as quarters. So Matt, which one is there more of? Are there more dimes or are there more quarters?
Dimes.
There are more dimes. Very good. Matt is always right. Sometimes I want to just get him to be wrong. So if we let x be the number of quarters, notice this is just if you were to lay them out and ask somebody, ask a little 3-year-old, count how many there are. There are the number of quarters. That 3-year-old probably couldn't tell you how much money you had, how many dollars you had, but she could tell you how many quarters. I don't know what I'm talking about, 3-year-olds. But there are 5 times as many dimes. So 5 times as many dimes. That would be the number of dimes. And then remember, for our overarching equation here, we don't need the number of dimes. We need the value of the dimes. So last time I checked, Matt, the dime was worth how much?
10 cents?
10 cents. And here's another important thing here. Notice our total value is given in dollars. So we want to write our 10 cents in dollars. So our value of our dime is going to be 10 cents, the rate, times the quantity of dimes, plus how much is a quarter? 25 cents. There's the rate, times the quantity. And that's going to give me my total value, which is 27.75. I shall solve it on the next page. And it wants to know, just before I go to the next page, it wants to know the number of dimes and the number of quarters. So again, taking a look at the equation, I've got the rate, the value of the dime, times the quantity of dimes, and the value of the quarter times the quantity of quarters. So if I asked you, what does this whole expression mean? This is the value of the dimes in dollars. And this is the value of the quarters in dollars. And this is the value of everything in dollars. Next page. Oh, sorry, I can't talk. So if I clean those up, I've got, oh shoot, what was my equation? It was 0.1 times 5, yeah? So 0.5x plus 0.25x was equal to, was it 27.75? 75. And so that's going to be 0.75x is equal to 27.75. And dividing both sides by 7.75, I get 37. That's nice. I was very worried I was going to have a fraction there. So there are, again, that x isn't the money that I have in dimes, because it'd be impossible to get 37. Well, that would be 37 cents. Yeah, okay. Anyway, and there are 37 dimes. And then how many? Wait, the x wasn't our dimes, was it? The x was our quarters. There are 37, excuse me. This is what's bad. I can't see my previous work. But there are 37 quarters. I defined x to be my quarters. And there are 5 times as many dimes, right? 5 times 37. Come on, Matt. I can do that in my head. 185 dimes. Am I right? Because I had no idea. And there's the answer to our problem. So hopefully these help you with the coin problems on the way. This is Angie. That's Matt-tastic. Wishing you good luck in your word problems.